And there's a plastic region shown in this color. I think it's maybe beige is a good name for it. So initially, we start out with a straight line from the origin to point A. So this is called linearly elastic region. From A to B, you still have an elastic region, but it's no longer linear. From B to C, you're going to have relatively large deformations due to shear stress on oblique planes. C to D is called strain hardening. The material shows more resistance. And failure starts at point D and ends at point E. So the biggest sigma you see on this figure, sigma U, is called the ultimate stress or ultimate strength. And sigma at point B is called sigma Y, yield stress or yield strength. Both of these are shown in our tables for various materials. So this is what I just mentioned. Sigma Y is yield strength, sigma U is ultimate strength. And these are our tables using SI units, followed by same tables using English units, which your book calls US customary units. So if you take steel, for example, you can see that ultimate strength sigma U is 400 megapascal for this first one listed here. And if you look at this table, we have 58 KSI. So that means 58,000 PSI, that's sigma U. Ultimate strength. If you remember from what we did last time, we take this number, sigma U, divided by factor of safety, and that gives us the allowable normal stress. So we stay way below sigma U. Do you have any questions about this diagram? Well, as you can see, we have start out with a straight line from the origin to point A. In all the problems that we solve in this class, we never go beyond point A. So we stay in the linearly elastic region. So linear means that sigma is a constant times epsilon, where the constant is the slope of this straight line from here to here. And that is called E, modulus of elasticity. So sigma is E times epsilon in the linearly elastic region. And this is called, oh, by the way, if you do the same for a brittle material like cast iron, then the diagram is going to look like this. You have a straight line, a little curve, and the material breaks without any warning. So sigma U is here, and this is Hooke's law. Sigma is E times epsilon again. For a straight line like this, sigma is E times epsilon, where E is the slope of this line.
E is PSI, PMA.
That's called Hooke's law. And as you can see, Mr. Hooke looks pretty scary because he is the person who came up with the equation like this, which also applies to springs. Force is spring constant times deformation. So this is Hooke's law. Sigma is E times epsilon, and E, which is the slope of this straight line, is called modulus of elasticity. We also find numbers for it in that same table. We just looked at. So if you go back, you can see this column here, modulus of elasticity in gigapascal. So for steel, E is 200 gigapascal. And in English units, it will be 29 million psi. Most of the problems that we deal with in this class are for steel. And so this number is used so many times that you remember that. 29 million psi, that's for steel. So here's the same table. I've highlighted the column that we're talking about, modulus of elasticity E, 200 gigapascal, 29 million psi. Those are for steel. Now this figure shows you that there are different types of steel. Pure iron, which doesn't have any carbon in it, is shown here. This is carbon steel 836. This is another one, high strength steel, and this is quenched and tempered. As you can see, this straight line has the same slope for all of them. That means E is the same for all of these different steels. So if you go back to our table, we have 200 gigapascal all the way down to here for different types of steel. But what's different is sigma U, which is the maximum sigma after which we have failure. Obviously, the sigma U's are very different. And you can see those numbers in our table. This is ultimate strength, megapascal. We have 400, 450, 550, 450, 760. These are all in megapascal. So sigma U's are different, but the E's are all the same for these different types of steel. Do you have any questions about this? Here's a table from a different book. This arrow points to modulus of elasticity E, 29 million psi for 200 gigapascal, which means 10 to the 9th pascal. These are for steel, and you have it for some other materials here. And this is yet another table for various alloys, concrete, plastics, and all of those things. So we have modulus of elasticity listed here in thousands of KSI, which means millions of PSI. Sigma is P over A. We saw that last time and also today. And epsilon is delta over L, called normal strength. And now we have Hooke's law, which states that as long as you stay in the linear region between this point and here, then sigma is E times epsilon. and E is the slope of that line, which we call modulus of elasticity. So if you do this, sigma is P over A, force divided by cross-sectional area, epsilon is delta divided by L, elongation divided by original length. And now we have Hooke's law, sigma is E times epsilon. So if we plug these into here, we will have P over A is E times delta over L. Sigma is P over A, epsilon is delta divided by L. So if we solve this for delta, we get P L divided by AE. So that's how we find elongation. And this equation is used many, many, many times throughout this course. So we're going to use it in a few examples today. This is the equation that I just wrote here. It's shown on the slide with the big arrow next to it. PL over A is used a lot. And first example, really a question. Structural member for which the properties such as E are the same in all directions is called isotropic. That means if you take a material like steel, E doesn't change with angle. It's the same horizontal direction, vertical direction, or at any angle. Some materials are not isotropic. Wood is a good example of that because the properties along the grain and perpendicular to the grain are usually very different. Here's a very simple example in which we are asked to find the force P for which a material steel rod with the dimensions shown here, which are diameter of 1/2 inch and length of 4 feet. We use 1 prime for feet and 2 for inches. And this is steel. So this number is what you're going to use for E. And we want delta to be 0.04 inches. And the question is, what force is required to cause this much deformation? Obviously, very, very simple problem in which we just take this equation and plug in the numbers and solve for P. So that means 0.04 equals P times L. And we always use inches in this course, not feet. So if dimensions are given in feet, we need to multiply by 12. So 4 feet converted to inches, that's for L. Cross-sectional area is pi over 4 d squared. And E is 29 million psi. So if you use standard units, which are pounds for force, inches for dimensions, psi for E and sigma, etc., then when you solve, you don't have to write out the units and cross them out or anything. When you solve for P, it's going to be in standard units of force, clearly pounds. Now you have the answer highlighted, 4744. So that was just a very simple example. And you have the solutions on the next slide. Questions about this problem? Here's another one. In which there's an elevator suspended by a 1/2 inch diameter, 100-foot long steel cable. 20 people with a total weight of 3,500 pounds enter. Obviously, the cable is going to stretch a little bit. Yes?
I have a question on the last one. What says 0.25 is?
I'm sorry?
Oh, never mind, it's that even there.
0.25 is radius, which is half of diameter.
Yeah.
So here, as we have 20 people entering an elevator, obviously the cable is going to stretch a little bit and the floor drops. And that's what we want to find. How far in inches does the elevator drop because of the additional weight of 3,500 pounds? So I'll let you do this using maybe 3-4 minutes, just to make sure that you can deal with units and everything, and you have the answer here, and we will look at the solutions after you're done. So there's the equation to use, and you have all the numbers on the slide. And here's B for steel. get the answer shown here? All you need to do is just plug in the numbers into this equation using inches and not feet. And E is 29 million PSI for steel. Did you all get the same answer? Area is pi r squared for circular rod cable, and radius is obviously half of the diameter, so it's going to be a quarter of an inch. Force 3,500 pounds. The length of the cable was 100 feet. Must convert to inches, so we multiply by 12. And in the denominator, we have the area in square inches, and E in PSI, and there's the answer, 0.74 inches. Questions about this problem? It's very basic, simple calculation. Now here's a problem which is a little bit more complicated. We have a rod shown here in the figure, and we are applying a 10,000 pound force at this point here to the left, 3,000 pounds to the right here. This is a leftward force, 2,000 pounds, and this is 9,000 pounds. Dimensions are shown. These are the lengths of 2 feet, 3 feet, and 4 feet. Cross-sectional area is 1 square inch. And this is steel. And we're asked to find the total elongation of this wire. If you look at the forces, they do add up to 0. So if you have a leftward force here of 10,000 pounds, this is another 2,000 pounds to the left, so we have 12,000 to the left, and we have 9,000 here to the right, and another 3,000, so that's also 12,000 pounds to the right. So we have equilibrium, and nothing moves, but each segment, which I've called 1, 2, 3, is going to elongate according to this equation. So what we need to do is find the deltas for piece 1, 2, 3, add them up. If you have tension, then the elongations are going to be positive. We have compression, then the elongations are negative. So obviously we need to keep track of what's positive and what's negative. So we're going to look at segments 1, 2, 3 separately. That means when we apply this equation, P is going to be internal force in that segment. And internal forces can only be found from free body diagrams, equilibrium, meaning statics. So we're going to make a cut somewhere in segment 1 and make a free body diagram of what's on the left side of that cut. So this is segment 1. And as you can see, we have 10,000 pounds here. That means we must have 10,000 pounds on the right side, so that we have equilibrium for segment 1. So that means the internal force in segment 1 is 10,000 pounds. So we could call that P1. And obviously this is in tension, so it's going to elongate. Then delta 1 is going to be a positive number. So delta 1 will be P1 L1 divided by AD. The A's and E's are all the same for all segments, so we'll just call it AD. Any questions about this piece? So the only way to find the internal force P is to make a cut and go all the way to the end, left side or right side, and enforce the equilibrium, meaning that the forces must balance. So if you have 10,000 to the left, you need the same thing to the right over here. No questions about this? So imagine a cut in the middle of segment 2. Now we have 10,000 pounds here. And then we have 3,000 pounds to the right. So we need 7,000 pounds here for equilibrium. So here's segment 2, and this was segment 1. So I made a cut in segment 2, and I looked at everything to the left side of the cut all the way to the end, and made a force balance to show that segment 2 is also in tension, and the force in it is 7,000 pounds, and delta 2 would be P2 L2 divided by 80. I'm sure you know what the next step is. We're going to make a cut in segment 3 and look at what? Everything all the way to the left or all the way to the right, whichever is easier. Obviously for segment 3, it's easier to look to the right. So cut here, segment 3. Here we have 9,000 pounds. So we need the same thing here for equilibrium. Now, if you make a cut in segment 3 and look all the way to the left, you get the same answer, but it's just going to be a little more complicated. It is essential to understand what we are doing here because this will show up in many, many problems for the next 10 weeks. No questions on this? All right, so we have all pieces our intention. The deltas will be positive for all of them, and we will end up adding the 3 deltas. This is free body diagram of segment 1, so that's this piece here, showing you that P1 is 10,000 pounds. L1 is 2 feet, clearly must be multiplied by 12 to get inches. Area, cross-sectional area was given as 1 square inch. And this is E of steel, 29 million PSI. And because we're using standard units for everything, we're going to find delta in standard units, which will be inches. So there is delta 1. Then we use the same equation using P2, L2, and P3, L3. So there is delta 2 using this force, 7,000 pounds. Then L2, which is 3 feet, converted to inches. For segment 3, we are using this force, 9,000 pounds, and the length is 4 feet. And we have positive deltas for all 3 pieces because they're all in tension. So we end up adding those 3 deltas, and you can see the answer at the bottom of this page. You have a question?
On delta 2, you use 3 feet, but with 1 and 2, it would be 5 feet. Would you just use the middle section, or would you use both of them added together?
We just use the length of that particular segment. So for segment 1, the force is 9,000 pounds, and we use 2 feet. For segment 2, we looked at everything all the way to the end in order to find the internal force in it, but then we will use the length of segment 2, which is 3 feet. And for segment 3, we use its length of 4 feet. Any other questions? We'll do this one, 2, and then we'll take a 10-minute break. No objections to that? I didn't think so. We have a structure here. There's a aluminum piece shown in blue and steel shown in light brown. They have square cross sections, and the dimensions are shown in millimeters. 50 by 50 for steel, 100 by 100 for aluminum. The lengths are shown here, 300 and 500 millimeter. These are the E's for steel and aluminum. So if we go back to our table, we have modulus of elasticity for steel 200 gigapascal, and for aluminum 70 gigapascal. So that's the source of these numbers. (200 gigapascal for steel, 70 for aluminum. And we want to apply compressive force here so that the entire structure shrinks in size by 0.25 millimeters. And the question is, how big a force do we need to do that? And yeah, you guessed it, going to give you a few minutes to work on this on your own. Did you say the internal force in the two materials are the same, or are they different? So if you apply force here, there will be a force at the support equal to that. We are neglecting the weight of this, both materials here. So if you make a cut here, and look at this piece, you conclude that the compressive force in it is P. Do you agree with that? If you do the same here, and you look at this piece, this is your free body diagram. So the compressive force is the same in both materials. So when you do PL over AE, the force P is the same for both materials. Clearly they have different L's, different A's, and different E's. And we know that the deltas are negative because we are compressing the structure. So if you want the magnitude of delta total, we have to do this twice. Add them up and set it equal to 0.25 millimeters. So P is the unknown, the L's are given, we can find the areas, E's are given, and you can just crunch the numbers. here are the numbers. We have delta 1 and delta 2. 1 is steel, 2 is aluminum. The force P is the same for both. So I factored it out and we end up with L over AE for piece 1 plus the same for piece 2. Delta is the quarter of a millimeter, so we need to divide by 1,000. Standard units are meters. P is the unknown. L is 0.300 meters for steel and 0.500 for aluminum. The areas are, these are square cross sections, so this is 50 by 50 millimeters. This is 100 by 100. Because each of these need to be divided by 1,000, we end up dividing by a million for the areas. And these are in gigapascal, so we need to multiply by 10 to the 9th. And then you get a big number in newtons, but if you express it in kilonewton, this is the answer you're going to get. Questions about this problem? As you can see, SI system is not always easier to use because the conversion from millimeter to meters, and you gotta do it more than once. So you end up dividing the area by a million. And the E's have a billion in them, so they could cause a little bit of complication. If we were doing English units with PSI, etc., we wouldn't have this problem at all. Questions about this example? Okay, let's take a 10-minute break and we will continue from here. If you walked in after I took attendance, I have marked you absent here, so let me know and we'll correct that. Next example in which we have the green member assumed to be rigid. And then we have two vertical members, A, B, and CD. These are identical in dimensions, in material. And we are applying the force here, and we want point D to move down by 0.01 inches. And the question is, how many force do we need to do that? So we have a rigid member. There really is no such thing as a rigid member. The forces are big, everything is going to deform. But when we say something is rigid, it means in comparison to the other members shown in blue, the deformations are very small. That means E for the green member is a lot bigger than E for the vertical members shown in blue. So what this means is that the green member is going to rotate, but it's going to stay straight because we assume it is rigid. And the unknown is the force G. And what we know is the downward movement of point E, which is 0.01 inches. So we need to make free body diagrams. which are going to be very sensitive for the vertical members. They are just in tension, both of them. So if you pull down at this point here, then this is going to stretch a little bit, and this point B is going to move up, so this is going to stretch also. So they will both be in tension, and so the free body diagram looks like that. This is the force in CD, which is this number, and the force in AB, which is this number. Tension in both. And this is a free body diagram of the member shown in green. We have an applied force P here, obviously must be shown. And if these members are in tension, this will be pulling up at point C, and this will be pulling down at point B. Do you agree with all this? Yes? So, from statics, we can write summation of forces in the y direction equals 0. That means this downward force FAB plus this downward force P must be equal to the upward force CD. We don't have any horizontal forces, so the force balance in the horizontal direction is useless. We can also write summation of moments about any point you choose equals 0. I've decided to do it about point C. So force times distance, that means P times 15 is equal to FAB times 10. One is clockwise, one is counterclockwise, and they must add up to 0. So that's this equation. And as you can see, we have 2 equations and 3 unknowns. The unknowns are FAB, FCD, and P. And obviously you can't solve for 3 unknowns using only 2 equations. So that means these forces cannot be determined using statics alone. That makes this a statically indeterminate system. So we need to look at deformations in order to get one additional equation. Then we can solve for all 3 unknowns. So if we jump forward, remembering that we always exaggerate the deformations a lot, the green member, which was initially horizontal, is going to stay straight, but it will rotate and look like that. So point E moves down by 0.01 inches. That was given. The member CD, which is this one, is going to elongate by delta CD. AB will also elongate by delta AB, and you're going to form an angle of theta here. So using the geometry here, you could get one additional equation. So given that these 2 equations came from statics, obviously this one says that FAB is 1.5 P. If you plug that here, we find that FCD is 2.5 times P. So the ratio is 2.5 divided by 1.5, which is 5/3. So elongations are force length divided by AE. Because the L's are the same, the A's are the same, the E's are the same, if the forces are related through this, the same applies to deltas. because delta is directly proportional to the force. So if the force in CD is bigger than the force in AB by a factor of 5/3, the same applies to their deltas or deformation. So we can find that delta CD is 5/3 times delta AB. And then here we look at this angle here. I call this L1 and that L2. Obviously, they add up to 10 inches, it's shown here. But if you look at this angle, tangent of this angle theta is delta AB divided by L1. From this little triangle, tangent of the same angle is delta CD divided by L2. So the ratio of deltas, which was 5/3, is the ratio of L2 over L1. Now we have two equations, two unknowns, and we could solve for both L1 and L2. Obviously, they add up to 10. That's shown here. And then if you look at this big triangle, tangent of the same angle theta, which is delta E divided by 15 plus L2, is also delta CD divided by L2, so that is shown here. This can be solved for delta CD. Once we have delta CD, which is FL over AE for that member, we could solve for force in it. And now we have two unknowns, two equations from statics, so we could solve for all forces, and P ends up to be 1,066 pounds. Questions about this? You need to spend some time on your own on the geometry to make sure you understand all the steps that we took in this problem. No questions? Here's another statically indeterminate problem in which there is a structure between two supports, A and B. So there's a floor and there's a ceiling. And we are adding a force P somewhere between the top and the bottom. And we want to find the reaction forces at each support. So we have this structure. If you apply force P here, this tries to push the structure into the ground, and the ground or the floor is going to oppose that, so it's going to apply an upward force to oppose P. So this is going to be the reaction force at support B. This is the force P. And the same force is going to try to detach this structure from the ceiling because it's pulling down, and the ceiling is going to oppose that too. So we are going to have an RA here. And from statics, we could write that RA and RB was added to P. So the net upward force is equal to the downward force. Can you write any other equations from statics? No, because there are no horizontal forces. And because all the forces line up, the moment balance will be useless. For example, if you make a moment balance about point B, all forces pass through it, so none of them has a moment about that point. So we have one equation which is highlighted in yellow, two unknowns, RA and RB. So once again, this is a statically indeterminate problem, meaning that we need to get one additional equation from studying deformations. Deformations are given by this. So we have to do this one segment at a time. One, this is two. Cut free body diagram. So if this is RA, we must have the same force here in the opposite direction in order to have equilibrium. So this is segment one. And if we do the same in segment two, meaning we make a cut here, this time it's easier to look at what's below it. So that would be like this. We have RB here. So we make the same thing here in the downward direction. So what this shows is that segment one is in tension and it's going to get longer. Segment two is in compression, so it's going to get shorter. The deltas must add up to 0, right? Delta one is positive, the other is negative, they add up to 0. So when we use this equation, for segment one, we use this force, RA, L1 divided by A minus RB L2 divided by AE equals 0. So when you're using this equation, this P here must be the internal force in the segment you're looking at. And that those forces only can come from statics. So RA for segment one, RB for segment two. The A's and E's are the same. So we could just get rid of both of these, and this means RA L1 is equal to RB L2. This is the additional equation that came from looking at deformations. Now we have two equations, two unknowns. Could easily solve for both RA and RB. And these are the deltas that I wrote here. Delta 1, delta 2. One is positive, one is negative. When combined, we get 0. And the highlighted equation came from statics. And we solve, and the answers are shown at the bottom of this slide. Any questions about this? No? We're going to solve the same problem using a different method, which is called method of superposition. I'm sure you've heard of this method in other classes. Superposition can be applied if we are dealing with linear equations, and we are. As you can see, delta is a linear function of P. If you double the force, you'll also double the elongation. So that's a linear equation, which means that we could do this problem in pieces and combine the results. This problem might appear to be a little complicated, even though it really isn't, because we have too many forces. There is RA, there is RB, and there is P. So what we're going to do is eliminate one of the forces. Obviously, we are not going to eliminate P because then there is no problem to solve. So I'm just going to remove RB and then we'll put it back. So we do this in two pieces. Eliminating RB means that we imagine that the lower support has been removed. No support, no force. So if that's the case, we're going to end up with this. The force P is applied here. Clearly, RB has been removed. So we have the same force P at the top in order to have equilibrium. So you can see that segment 1 is being stretched by force P, and segment 2 doesn't deform at all because there is no force applied to it. So delta 1 will be PL1 divided by AE, as shown here. Then we're going to put back what we removed, which was RB. So if you put RB back here, then we will have support reaction here equal to that, and the entire structure will be compressed by that force. So delta 2 will be negative RBL divided by AE. And the next step is that we set delta 1 plus delta 2 equal to 0. So PL1 divided by AE minus RBL divided by AE is 0. Could easily solve for RB, and we have another equation from statics which gives you RA, and clearly we get the same answers as before. Questions about this? No? And this is the last problem for today. We have a member shown in blue, which is assumed to be rigid. Maybe you know what that means. There are two wires, A, B, and C, D, shown in brown. They are identical, same length, same material, same cross-sectional area. And the distances are shown here. All the dimensions are lowercase a, and we don't need to know the numerical value of that. We are applying a force of 50,000 pounds in the downward direction, as shown here. This is a frictionless pin. Again, rigid means that the blue member doesn't deform relative to the deformation of the wires. And you see a free body diagram for that member shown here. Obviously, we need to show the applied force P. This is going to cause tension in both wires. So the wires are being pulled down, and they will be pulling up, as shown here, FCD for this wire, FAB for this wire. And this is a pin assumed to be frictionless. There is no force in the horizontal direction because there are no other forces in the horizontal direction, so this must be zero. But there will be a vertical reaction at pin O. I've called that OY. Here's the summation of forces in the vertical direction, meaning OY plus FAB plus FCD must be equal to the downward force P. And this is a moment balance about point O, force time distance. So we have FAB times A plus FCD times 2A equals P times 3A. The moment that these forces are going to be counterclockwise or positive, this is going to be clockwise. So as you can see, we have the same situation again. We have two equations and three unknowns. The unknowns are OY, FAB, FCD. So this was the statics part of it, and once again, we have a statically indeterminate system. So we need to look at deformations to get one additional equation. What can you say about deformations in this problem? The blue member is assumed rigid, so it doesn't deform, it stays straight. The wires are going to be stretched. They are both in tension. But which one stretches more? CD, right? How much more? Twice as much, because it's twice as far from the pin. In other words, if we look at the system after it deforms, this is deformation of AB, delta AB. This is delta CD. Tangent of this angle is going to be delta AB divided by A. And it's also delta CD divided by 2A. So that means delta for CD is 2 times bigger than delta of AB. Do you agree with that? Same angle, same tangent. So delta AB divided by lowercase a is equal to delta CD divided by 2A. So delta CD is twice as big because deltas are directly proportional to the force. The force in CD will be twice as big, right? Same material, same dimensions, lengths, cross-sectional area. If you wanted to stretch twice as much, the force in it must be twice as big. So there's your additional equation. FCD is 2 times FAB. This comes from studying deformations. Now we have 2 equations and 2 unknowns. We have 3 equations and 3 unknowns, so you could solve for all the forces. These are the forces. FAB, 30,000 pounds. FCD is twice as big. The cross-sectional areas were given as 3 square inches. And sigmas are P over A, or force over area. So we have 10,000 PSI for AB and twice as much for CD. Questions about this problem? Well, this is where we ended up this morning for the 8 o'clock class, so I'm going to stop here. And have a great weekend. I'll see you on Tuesday.